Welcome, Sec Math 3 students. We are ready to start a brand new chapter. This is chapter 5. We're going to be talking about, to begin with, the natural base E. And Leonard Euler is how you pronounce his last name. It's Danish, who lived in 1707 to 1783. He discovered E. Actually, he's not the first one to use E and discover it, but he's the one that gave it a name. And so he decided to name it after himself. And so therefore he gave it the name of E, which is pretty cool. Well, what is the number E and how did mathematicians discover it? If you take, there's several different ways that you can do it, but here's one example. If you take this equation, which is 1 plus 1 divided by x, that whole amount that's in the parentheses raised to the x power, then notice what happens as we do that. So as we put 10 in place of x here in this fractional part, so it'd be 1 plus 1/10. So 1 and 1/10 raised to the 10th power, we get 2.5937. By the way, please follow along with me as I'm going through this. This starts on page 9 in your brand new workbook for semester 2. And if you don't have the workbook yet, you need to come in and pick it up from us, from your teacher. And for those of you that are my students, I've inserted a blank copy of it in Canvas for you to pull up if you haven't picked up the workbook yet. Okay, so this is on page 9. I'm filling in this table, this table of values. If you were in class, we'd be doing this in class. So now I'm going to put 100 in place of x. So I've got 1 plus 1 over 100, or 1 and 1/100th. And we're going to take that to the 100th power, or the 100 power. And you get 2.7048. And then we'll do the same thing with 1,000, and then 10,000, and then 100,000, and then 1,000,000. So we'll keep making those numbers get larger and larger and larger. And as we do that, notice that it approaches 7.1828 and so on. Okay, so there is a little video clip that you can watch, and the location of it is on YouTube, and the URL location is on the bottom of page 9. So I would suggest you stop this video, watch that one, so you can find out where we use the number E in mathematics. It's we don't just use it in math, we use it in chemistry and physics and a lot of different places, in statistics, in accounting. So it's used in several different places. And wouldn't it be cool to be able to discover a number like E? By the way, E is an irrational number like pi is as well. It goes on forever when you put it into decimal form, and there's no repeating pattern at all. Okay, another way that you can derive the number E is by doing this. You take 1 plus, and then 1 divided by 1, and then plus 1 divided by 1 times 2, plus 1 divided by 1 times 2 times 3, plus 1 divided by 1 plus 1 times 2 times 3 times 4. Make sure that this is all in the denominator. So if you did this on your calculator, you'd want to make sure you put the stuff in the denominator inside parentheses. And now what you want to do is locate where the number E is found on your calculator. So on the TI-84 calculator, if you look right above the division sign, you're going to see it on the right-hand side. It is in blue on my calculator. It could be in a different color on yours. But that means that you would have to hit the second key in order to get the value of E. And you could just go second and then the division symbol. So that gives you E, and then enter, and it'll tell you the value of E, which is 2.71828182846. By the way, this is one of the questions on the homework, is taking E to the 9th decimal place. On Desmos.com, you can simply type E, the letter E, into the box on the left-hand side, like if you went into the graphing portion of it, and you're going to see the value of it. This is a screenshot from Desmos that just pops up. And also, I wanted to go back to the TI-84 for just a minute and tell you that there is also an E raised to a power key that is on the left-hand side of the calculator. It's right above the Lin key, which is LN. And we're going to be talking about Lin in this chapter, along with log, which is right above it. So this chapter we get into logarithms. And e to the x is the inverse function of Lin, which is log base e. And so that's on the left-hand side. So again, you would type in second and then the Lin key to give you e to the x, and then you could take it to certain powers to do that. Okay, so let's go on to the next slide. Okay, so the first thing that we want to do is on page 10 now, under exploration number 1, is you want to fill in the table that is provided for you. Now, I made my table here in this slide presentation go vertically, where the table that you're given in the workbook is a horizontal table, but it's still the same values. So we are given the values of x being -2, -1, 0, 1, and 2. So we're going to plug that up here in the exponent. So again, on your calculator, you could use that e to the x key on the TI-84 and plug in each of these numbers here to get the values over here in the y column. Or on Desmos, you can just type E and then the exponent key, which is right above the number 6, is the exponent key. So you go E, shift 6, and then you type in these numbers for x right here to find out what the value is, and then just press enter. So notice that when x is -2, we get that y is about 0.135. When x is -1, we get that y is about 0.368, or about 0.4, really close to 0.4. When x is 0, anything to the 0 power we know is 1, so it goes through 0, 1, and that's a common point on exponential growth or exponential decay equations before we start manipulating it, before we shift it to the right, left, up, down, or we put a number in front of it. It goes through that 0.01. And then when x is 1, notice that y is about 2.7, so right up here. And when x is 2, then we're off this graph that you can see, but it's up here at 7.389. Let's talk about the domain and the range for just a minute of the graph. So notice that this graph, as I move across the x-axis, I can always look to the left as I'm walking along the x-axis or driving along the x-axis. I can look to my left and I can see that there are always points on this red graph all the way across. Even up here, as I get closer and closer to positive infinity, I'd have to look up quite a ways to my left, but I would still be able to see points because this continues to go up and out, up and out, up and out forever. So my domain is all real numbers. In other words, it's negative infinity to positive infinity. That means all real numbers. And the range is from 0 to infinity. And let's see why. As I walk up the y-axis from the bottom to the top, notice there aren't any points to the left or to the right of this on that red graph. Not until I get above 0. Then when I'm above 0, I can look out here to the left, and there's always going to be points. And then as I continue on up the y-axis above 0, there are always points on this red graph. Notice that the line y equals 0 or the x-axis serves as an asymptote. So this graph, as the values of x come out here towards negative infinity, it gets closer and closer to 0. Okay. All right. Now let's look at the graph of y equals e to the negative x. Okay, so now in place of x, I'm putting negative 2. So notice that this would be e to the negative 2, which is e to the positive 2, which is 7.4. And then when I put negative 1 in there, this is e to the negative 1, which is e to the first power, or about 2.7. Notice I'm just rounding off to the tens place. Since we're graphing, it's easier to just take numbers to the tens place when you're graphing. Okay, when x is 0, I would have e to the 0 power again, which is 1. So here's e to the first power, or e to the 0 power, which is 1. When x is 1, now it's going to be e to the negative first, which is 0.4 approximately, so right up here. And when x is 2, I've got e to the negative second, which is about 0.1 on my graph, so about right in here. And you can see at negative 1, it was 2.7. So it kind of flips across the y-axis, the graph that we just did of y equals e to the x. Notice that my domain is still going to be all real numbers. So as I'm moving from the left out here toward of negative infinity towards positive infinity on the x-axis, I can always look up here to my left and I see points on this red graph all the way across. So therefore, it's all real numbers. Again, the range is still starting at 0 and going to positive infinity because there aren't any points down here on the red graph that are below the x-axis, below where y equals 0, right here. And again, that line y equals 0 or the x-axis is a asymptote that the line approaches or the graph approaches. All right, so let's summarize what we just talked about. And this is down at the bottom of the page 10, and it's also again on the top of page 11. It says natural base functions, a function of the form y equals a times e to the rx is called a natural base exponential function when a is greater than 0 and r is greater than 0, then the function is going to be exponential growth. It goes up to the right, okay, like our y equals e to the x that we just did. Notice it goes through 0, 1. And then if I take where a is greater than 0, so it's a positive number again right here, but this time I take when r is less than 0, like we did on the second graph, where we let x up here be negative x. So in other words, our r is negative 1 right here, negative 1 times x. Then we get exponential decay. It's going down to the right. In either case, our x-axis serves as a horizontal asymptote that the graph approaches. Both graphs go through the point 0, 1. Okay. And the domain on both graphs is all real numbers. As you move from left to right, you can always see points on that graph. Okay, and the range on both graphs again is starting at 0. We don't see anything below 0, and then all the way up to positive infinity. Now we're going to manipulate these graphs. We're going to start to make some changes to it. So what do you think is going to happen if we made a negative? So we only talked about when a is positive. But now what if we make a negative? So the number that comes in front of the e, if that's negative, what do you think is going to happen? Okay. So let's go on to the next slide and we will see. Let's see. I need this to move. Okay, so what do you think is going to happen when we graph y equals 2 times e to the x? So this is, oops, I think I typed that in wrong. I did. Okay, that should have been 2e to the negative x. I'll see if I've got the right graph that goes along with this, but this should have had a negative sign right here. So we'll see what graph I have as we plug this in. So we know that y equals e to the negative x is exponential decay. It goes down to the right, like that. If I put a 2 in front of it, what that is going to do is make it just decrease and decrease at a quicker rate. But as we go towards negative infinity on the x-axis, it's going to increase at a quicker rate. So let's just tap and see. Nope, I typed the wrong equation in here. I typed this one, 2e to the x. So that is not the equation that is shown on your A. So you could change your A to just be y equals, you change your equation to say y equals 2e to the x, since that's what I have pictured here. Okay, let's go on to the next one. Okay, what do you think is going to happen if I put a 0.75 in front of it? So that's like 3/4 right here. So that would slow the rate down, but it's still positive. So it's still going to go up to the right. And here it is. Here's the graph. Still goes up to the right, but notice that it doesn't go through the 0.01 anymore. Now it goes through the 0.0 and 0.75. Because when x is 0 right here in the exponent, I'm going to have 3 times 0, which is 0, and e to the 0 power is 1, times 0.75 would be 0.75. So that's this point right here. So this 3, though, is making it increase at a pretty rapid rate because you're timesing x by 3 before you're taking e to that power. So notice that it has a much quicker increase than the graph that we did before of just y equals e to the x. Okay, so that was example 1b. So now let's look at example 1c. So this is negative 2e to the 0.5x. So let's talk about what we think is going to happen. That negative 2 out in front of it, I think what is going to happen by putting that negative sign there is it's going to reflect it. I think it's going to reflect it down across the x-axis. The 0.5 in front of the x will make it so that it increases, or in this case, it's going to look like it's going down because it's reflected down across the x-axis. So it's going to decrease at a less steep rate because we're dividing whatever x is in half, right? We're timesing it by 0.5 or 1/2. Okay, so let's pull up the video and see or the graph and see if I was right. Okay, so yeah, it's reflected down across the x-axis. Notice that my y-intercept is now down here at 0, -2. So when x is 0 up here in the exponent, I have 0 times 0.5 is 0. E to the 0 power is 1. 1 times -2 is -2, which is down here. And you can see that it is increasing at a less, or decreasing at a less steep rate than our graph of y equals e to the x because of that 0.5 in front of it. All right, so now before we go on to example 2, what do you think is going to happen if we add or subtract a number in the numerator, or if we add or subtract a number after, let's see, after the e to the rx part? So think about that, and let's think about what will happen. Okay, and that shouldn't say in the numerator, that should say in the exponent. So if we add or subtract a number in the exponent, is what that should say. What would happen to the graph? Okay, so let's go on to example 2. Let's see. Okay, so we are 2a. We want to graph y equals e to the x, and then we're going to subtract 4 from that. So what do you think is going to happen? It's similar to the graph of y equals e to the x, but I've got a -4 outside there. I think that what is going to happen is it's going to take the graph of y equals e to the x and it's going to shift it down 4 units. So let's see if I was right. Yep, notice that my horizontal asymptote is no longer the x-axis up here. It's now been shifted down to where y equals -4. Okay, because after we find the value of e to the x, then we're going to subtract 4 from it. So instead of going through the point 0, 1, which the graph of y equals e to the x did, it's now shifted down 4 units, and it goes through 0, -3. Okay, so let's go on to the next one. This is example 2b. So if I put a 2 in front of the e, that's going to make it increase at a quicker rate. It's going to go up and to the right, so it's going to be up to the right. And then if I put this +1 up here in the exponent, I think that's going to shift it to the left 1 unit. Okay, so let's see what happened. Okay, sure enough, notice that instead of going through 0, 1, it's shifted to the left 1 unit, but because of the 2 in front of there, it's now 0, 2, or it's -1, right? 2, -1, 2. So let's think about if we put a -1 up here in place of x, -1 plus 1 is 0, and then e to the 0 power is 1, and 1 times 2 is 2. So when x is -1, y is 2 right there. Okay, it's still an exponential growth. You can see that. And it's been shifted to the left 1 unit. Okay, next graph is y equals a negative in front of the e to the x and then +2. So think about what is happening there. I think that what happens is the negative sign in front of the e is going to reflect it down across the x-axis. So instead of going up to the right, it's going to go down to the right, and it'll be below the x-axis. But that +2 right there is going to shift my horizontal asymptote up 2 units. So instead of my horizontal asymptote being at y equals 0, it's now going to be at y equals 2. Let's see if I was right. Yep. Okay, so it's reflected down. Instead of going up to the right, it's now going down to the right. And notice my horizontal asymptote of y equals 0, or the x-axis, has been shifted up here to y equals 2. Okay. How did the domain and the range change? Notice my domain on this graph is still all real numbers as I move across the x-axis. Then I can still see points on that red graph all the way across as I'm going across the x-axis. There's always points either to the right or to the left as I move across. But now notice my range has changed. My range now, notice that it goes down towards -infinity. Off of the y-axis, there's always points on that red graph until I get up to the number 2. And then above 2, as I look out to the right or to the left, there aren't any points on that red graph because it just approaches the line y equals 2 as it goes out towards -infinity. So my range is what really changed on this graph. It's now -infinity to +2 is what the range would be. Okay, that's the end of this portion of the video. The other portion you will watch in video number 2.